Okay, so we're going to continue on with some more thermo. Now we're going to talk specifically about enthalpy delta H, or H. H is just what we use to as the variable for enthalpy. Basically, all it is the sum of the internal energy of the system and the product of the pressure and the volume. Now, in the very first part 1 video, we've talked about P, we've talked about V, and those relationships. So delta H, and also, by the way, we're going to have a ton of different delta H equations, which just kind of mix up different parts, how we can mathematically associate them. Kind of like if I said A equals C and C equals D, I could say A equals D, kind of like that. So enthalpy change is the change of that energy of the system and the product or the pressure and volume. So we can say that delta H of the reaction is equal to Q the reaction at constant pressure. That's the kicker there, constant pressure, okay? Usually delta H and delta E are very similar in their value, but they mean really two different things. So the difference, this is the takeaway here, the difference is the largest for the reactions that produce or use large quantities. So the larger the quantity or the larger the product, the larger the difference between delta H and delta E are going to be. So when delta H has a negative value, so for example, maybe it's negative 32 kilojoules. Okay, I'm just making up a number. When delta H is negative, that negative sign tells us that it's an exothermic reaction, that heat is going from the system into the surroundings. Things will feel warm to the touch, okay? When delta H is positive, if delta H was positive 32 kilojoules, then we would know that this is endothermic, or heat is going into the system from the surroundings. It's going to feel cold. Your best example of this one are those, if you've ever played a sport and you have those the Insta packs, you twist your ankle or something like that, you crack the bag and it turns cold. That is because it's feeling cold. A really, really good example of exothermic, which sadly this semester you won't get to experience this actually in a lab, but an acid-base reaction is exothermic, and your test tube would feel warm. Okay, so exothermic, the outside temperature rises because heat is going from the system into the surrounding. The endothermic, the surroundings are cool because heat is going from the surroundings into the system. Exothermic is when we form new bonds. This is the exothermic part. The breaking of the bonds is the endothermic part of a chemical reaction. So for endothermic and breaking the current existing bonds between elements in a compound, we have to put energy in to break those bonds. When the new products form, energy is released, and that process of the reforming of the bonds is exothermic. And so whether or not the overall reaction is endo or exothermic depends on the difference between the two. So if there's way more energy needed to break a bond than there is to form a bond that is, that's released, then overall it's going to be endothermic. If there's way less energy to break the bonds and way more energy released in reforming of the bonds, then overall it's going to be exothermic. Okay, so let's look at this, exothermic versus endothermic. So it says identify each process as endo or exothermic. indicate the sign of delta H. So let's look at these. So sweat evaporating from the skin, okay? If sweat is evaporating from the skin, it's endothermic. Why? Anytime we evaporate something, just think of like boiling water, right? If you have liquid and you're vaporizing it to steam, you're putting heat into that system, just like a pot of water on a stove, okay? So in the same way, sweat evaporating from the skin means heat is going into that sweat and evaporating it off. All right, so it's an endothermic. If it's endothermic, positive delta H. Water freezing in a freezer. Well, water freezing releases heat, and therefore it's exothermic. Negative delta H. Okay, wood burning in a fire. That should be pretty obvious. Exothermic. And negative delta H. So the enthalpy change in a chemical reaction is an extensive property. Okay, so what does that mean? That means the more you use, the larger quantity that's there, the more enthalpy change is going to occur. So you can calculate the enthalpy change based on, well, let's just look through this example and talk about it. So we have a combustion reaction here, C3H8 plus 5O2 yields 3CO2 plus 4H2O. The overall delta H for this reaction is negative 2044 kilojoules. So that makes this an exothermic reaction. That should make sense considering it's a combustion reaction. Now, I can say 1 mole of the C3H8 is equal to this kilojoule, which is the overall total. I could say 5 moles, this 5 is coming right from the coefficient from the balanced chemical equation, is equal to the negative 2044 kilojoules. But for it to be 1 mole of O2, I could say that that's negative 2044 divided by 5. And that would be, for 1 mole of O2, that would be negative 408.8 kilojoules, okay? When we have the overall delta H of the reaction, it applies for the 1 mole, including the coefficient, so this would be 1 mole, 5 moles, 3 moles, 4 moles, etc. Okay, it would apply for the whole number. If you're asked specifically about 1 mole of that entity, you have to divide the overall number by whatever coefficient is in front of that compound or element, okay? So let's look at this. An LP gas tank in a home barbecue contains 13.2 kilograms of propane, C3H8. Calculate the heat, which immediately tells you delta H, or Q, depending on what we're doing, associated with the complete combustion of the propane in the tank. So that's what we're given, and we're finding Q. So we're going to use delta H to find Q. That's the relationship. So conceptually what we have to do is we have to get to moles of the propane. Okay, we're going to go from kilograms, which was given, and we're going to convert that to moles of the propane. Okay, once we have that, we can now use the delta H that was given to figure it out. So let's look at the math. So here's my kilograms to grams to moles using molar mass of the propane. And then it's always, one of the things I forgot to say is that when you have a delta H, it's always assumed that it's kilojoules per 1 mole. Okay? So we got to know how many moles there are of the C3H8 in that 13.2 kilograms. So once you do the math, multiply the whole top together, divided by the whole bottom, multiply together, it's going to be negative 6.12 times 10 to the 5th kilojoules. So that's the Q, or heat, that is given off by that 13.2 kilograms of the propane. All right. Ammonia reacts with oxygen according to the equation, blah. Calculate the heat in kilojoules associated with the complete reaction of 155 grams of NH3. Okay. Go ahead and pause it here. See if you can work it out. All right, so here's the answer. Okay, first thing we're going to do is we're going to convert it to moles. The molar mass is 17.039 grams for 1 mole. Okay, and then we're going to use this and say I want to get rid of moles of NH3. And that's how I'm going to set it up. So when I do the math, minus 17. Okay, I get negative 8, 2, 4, 1.68. But now we have to divide by 4 because of that right there. And so it's negative 2.060 kilojoules per 1 mole. Okay. If we wanted the total, we would have not divided by 4. If we're looking for just 1 mole, we don't divide by 4. If we do want 1 mole, based on this 155 grams, we do divide by 4. Okay, so calorimetry, it's basically just mixing 2 different things, hot and cold, we often use coffee cup calorimeters. They're just those styrofoam coffee cups that are double stacked, and then there's a lid. We actually, in our lab now, we have actual styrofoam calorimeters that have a lid that has a really good seal, so we lose as less heat as possible. It's not perfect. It's not like it's a bomb calorimeter or in a vacuum, but they're pretty good compared to like the coffee cup. So the takeaway here is that Q of the reaction is going to be equal to negative Q of the solution. That is our big go-to. Okay. So delta H of the reaction is equal to Q when it's at constant pressure, and that's equal to Q of the reaction. Okay. To get delta H of the reaction, per mole of a particular reactant, this is when we're back to dividing by the number of moles that are right from the balanced chemical reaction. So let's look at this example. Magnesium metal reacts with hydrochloric acid according to the balanced equation. There it is. In an experiment to determine the enthalpy change for this reaction, you combine 0.158 grams of magnesium metal with enough hydrochloric acid to make a 100 milliliter solution in a coffee cup calorimeter. The hydrochloric acid is sufficiently concentrated so that the magnesium completely reacts. So all of this gets used up. There won't be any left over. The temperature of the solution rises from 25.6 degrees Celsius to 32.8 degrees Celsius. So the delta T for this reaction is 7.2 degrees Celsius. Okay? Find delta H of the reaction for the reaction as written. Use 1 gram per mil as the density of the solution, and the specific heat, you're assuming it's the same as water, 4.184 joules per gram degree Celsius. So this is what we're given. All the information. We just found out delta T, just by simple subtraction, is 7.2 degrees Celsius. So what's our plan? Conceptually, step 1, we're going to use this. Why? That gives us our Q. Then we know for step 2 that Q of the reaction is equal to negative Q of the solution. Note, when we're using Q equals MC delta T, that is for Q of the solution. Okay? So whatever our answer is here, we're going to flip the sign. Same number, just flip the sign. Now, another delta H reaction or equation. Delta H of the reaction is equal to Q of the reaction divided by the moles of magnesium. So we're going to have to take that 0.158 grams of the magnesium and convert it to moles using molar mass. So here's the math. We were given this. The mass of the solution, we're going to use the density to find the grams. So it was 100 mils. And they were told us to use that density, the 1.00 grams per mil, to find the mass. So that's how we're going to find the mass of the solution. We already solved for delta T in the beginning. So now we're just going to take all these numbers. We're going to take this, this, and this, and just plug it into the first equation. Okay? So 1.00 times 10 to the 2 grams times 4.184 joules per grams degree Celsius times 7.2 degrees Celsius. When you do the math, this is what you get. Okay? Now, part 2 was that Q of the reaction is equal to negative Q of the solution. We had a positive Q of the solution here, so we're just going to go ahead and throw that negative sign up in front of it. Just flip the sign. So now, I like to solve for moles first and then plug it into step 3. They have done it just all on the bottom here. So this can be done as a separate step. That's totally fine. I prefer to do it that way, in fact. So once you have your moles, you just simply take your Q of the reaction divided by the moles of the magnesium, and that's your final answer. All right, so we can have a lot of examples of ways that there's different relationships with delta H of the reaction. So enthalpy, the numerical value of the delta H, it's very specific to each reaction. And not even just each reaction, but the conditions of that reaction. So because of this, that makes enthalpy an extensive physical property. Okay, when a reaction is multiplied by a factor, delta H is multiplied by a factor. So for example here, if I had this elementary step, solid carbon plus oxygen gas yields carbon dioxide, there's my delta H. If I multiplied all of this by a coefficient, you'll see why in a few minutes, if I multiply all this by a coefficient, then the delta H has to be multiplied as well. Okay, if the reaction is reversed, let's say we flipped this, if we flipped this to get that, then we have to flip the sign. Why does this matter? Hess's law. Okay, so we're going to go through this. These aren't difficult, they're just lengthy. All right, so the whole goal here is that you'll have one reaction, and this is your overall reaction. Okay, and this overall reaction occurred stepwise, meaning in many steps. Okay, in this case, it happened in 3 steps. Okay, now, in order to figure out what's going on with the delta H, we're going to have to flip some of these, multiply some of these, because we're going to want some stuff to cancel out. We want to make sure that all of these steps matchy-matchy to the overall reaction. So let's just talk about this as we go through it. So if we look at the very first reaction here, okay, and actually I'm going to call this, I'm just going to number these so it's easy to keep track. So these are our 3 stepwise reactions. If I look at stepwise reaction number 1, you'll see the C3H8 is on the reactant side of this equation here. But in the overall, it's on the product side. So what that means is I need to flip that reaction. And for purposes of right now and me being lazy, I'm not writing the states. And because I flipped it, I got to flip the sign of delta H. Okay? All right, now I'm going to look at number 2. I got carbon on the reactant side and carbon dioxide on the product side. Okay, carbon on the reactant side. We're matched up. We're good to go. But there's a 3 in front of that carbon. I don't have a 3 in front of this the carbon in number 2. So now I'm going to not flip it. I'm going to keep it the same, but now I have to multiply the whole thing by 3. Okay, 393.5 times 3. So that new delta H is negative 1180.5 because I had to multiply it by 3. All right. Third one. Okay, I got H2 on the product side or on the reactant side, O2 on the reactant side. Okay, but my H2, that's what matches. But there's a 4 in front of the H2. I only got a 2 in front of my H2. So I'm going to have to multiply everything by 2. Okay? Don't need to flip it because everything's in the right spot. And the new delta H is negative 967.2. Okay, now what we have to do last is just double check that any intermediates will cancel out so that all I'm left with is the carbon, the H2, and the propane. Now, by intermediates, what I mean is that in many of these stepwise reactions, one thing is produced in one step and then used up in another step. Those are intermediates. All right, so we got a lot of intermediates here. So let's look at what we got. Okay, do we need the carbon dioxide? It is not in the overall reaction, and therefore we don't. So this carbon dioxide will cancel out with that carbon dioxide. Those are an intermediate. Okay, it was used in one step, produced in another. We can cancel out with these three equations across the arrow and combine top and bottom. Okay, so got rid of my carbon dioxide. All right, water. Is water in my overall reaction? It is not. So I got 4 waters here. That's going to cancel with these 4 waters there. Okay, now the propane C3H8, yep, got to keep it. Got to keep it right where it is because that's in the overall reaction. All right, oxygen, not in the overall reaction. So that'll cancel out. That's 5O2. I got 3O2 here and 2O2 there. That makes 5O2. So they both cancel out with that 5O2. All right. Carbon, 3 carbon. That's got to stay because that's in my overall reaction. H2, 4H2. Yep, that's got to stay because it's in my overall reaction. So, I did it correctly. At the end, I have 3 carbons plus 4 hydrogen gases gives me C3H8. My overall matches the work I've done to rearrange my stepwise reactions. So now the question is, what is the delta H for the overall? All we do is simply add up these numbers. So 11.8, 0.5 plus 2043. So the overall delta H for this reaction is negative 104.7 kilojoules. And this is how you do Hess's Law. Okay? I put a whole video up of worked problems just on Hess's Law. Please go watch it. I highly recommend practicing these as well.